I'm going to take you through a couple of practice problems using the Hardy-Weinberg equations. So let's just review the equations to start with. Remember that if we are looking at the allele frequencies, we can use the equation P plus Q equals 1. P represents the frequency of the dominant allele, whereas the Q represents the frequency of the recessive allele. So basically what this means, if we know the frequency for either of those alleles, we can solve for the other pretty easily because they have to add up to equal 1. The equation for the genotype frequencies is the p squared plus 2pq plus q squared equals 1. And we know that p squared represents the frequency of the homozygous dominant individuals. The 2pq represents the frequency of the heterozygous individuals. And then the q squared represents the frequency of homozygous recessive individuals. So if we were to use our allele symbols, the homozygous dominant would be something like a big A, big A. The heterozygous would be a big A, little a, if that's our allele symbol. And then the homozygous recessive would be a little a, little a. So we're going to work two different types of problems to go both directions. We're going to, in one problem, we'll assume that we know the genotype frequency, and then we'll use it to calculate the allele frequencies. In the second problem, we'll go the other direction. Okay, so let's start with a problem where we know the genotype frequencies, and we can work through how we can use those to calculate the allele frequencies. So here we've got a population of pea plants, and we're looking at the color of the flower, and that is coded for by a gene that we can have two variants of. So we can have an allele that codes for purple flowers, which is dominant, and we can have an allele that codes for white flowers, and that would be recessive. So if we were examining a patch of these pea plants and we had 36 purple flowering plants and 64 white flowering plants, that means we have a total of 100 plants. So let's write that down so we can use that. If we have a total of 100 plants, we want to focus on the ones that are white flowering. The reason we're focusing on these is that the white is the recessive trait. So we know that the genotype for these 64 individuals is homozygous recessive. And remember that homozygous recessive is our Q squared portion of our Hardy-Weinberg equation. So in this population of 100 individuals, if 64 of them have white flowers, then we can do the frequency pretty easily. It's 64 divided by 100, and that is 0.64. And that 0.64 is also equal to our Q squared, okay? So if we know Q squared, we can solve for the value of Q, and Q is our allele frequency for the recessive allele. So we can do that by taking the square root of 0.64. So Q would equal the square root of 0.64, and that's going to equal 0.8. So now that we know Q, remember that P plus Q equals 1. Okay, so if we know that the value of Q is 0.8, then the value of P has to be 0.2, right? Because 0.8 added to 0.2 would give us 1. So if Q is 0.8, then it would hold true that P is equal to 0.2. And so that's how we can use the genotype frequencies to calculate allele frequencies. So in this last problem, we're going to go the opposite direction. We're going to use allele frequencies to calculate genotype frequencies. So in this case, we're given information about two alleles, a dominant and a recessive, and we're told that the frequency of the recessive allele is 0.1. Well, if we remember our P plus Q equals 1, the recessive allele is denoted by the Q, so we basically know that Q is equal to 0.1. And if Q equals 0.1, we can figure out what P is because P plus Q have to add up to be 1. So if Q is 0.1, then P has to be 0.9. And I know that because I take the 1 minus 0.1, and that gives me 0.9. So the P equals 0.9. Once we know the frequency of the P and the Q, we can then use the equation of the P squared plus 2PQ plus Q squared equals 1, and we can go ahead and calculate the frequencies of individuals with the genotypes listed. So the homozygous dominant genotype, that is going to be our P squared, and so that would be equal to 0.9 squared, which would give us 0.81. The heterozygotes, that relates to this portion here, the 2PQ. So to calculate the frequency of heterozygotes, we would have to say 2 times 0.9 times 0.1, and that should give us 0.18. Then lastly, to calculate the frequency of the heterozygotes, which is our Q squared, we're just going to take our value of Q, which is 0.1, and we square it, and that would give us 0.01. So that's how we can start with the allele frequencies and use that information to solve for the genotype frequencies. And those two problems give you a good example of the different types of questions that you'll be answering on your quiz and exam.